Wednesday for reasons that you don't have to understand. I've started to grade the first 3 problems, and there were mixed responses. So many of you, too many of you, forgot that the Laplace transform of a PDF evaluated at s equals 0 is equal to, he gave the answer. What is it? 1. A star of 0 is 1. Z transform of a probability set of distribution, mass function, at z equals 1 is equal to 1. And those are equations you needed to get those constants I was asking for. But some of you needed to use a better strategy for buying points, too. If you couldn't get a 2-point part A, on which the rest of the problem depends, give up the 2 points and get the answer. So I didn't teach you strategy of how to buy problems, but anyway, we'll see the results. It turned out to be a harder exam than I thought it would be. Wasn't meant to be hard. As I say, the grades may be not great, but remember I'm going to grade the final letter grader for the course quite leniently, so I'll keep that in mind. Okay, here we go. Lecture 10. Let me review again for you. Yes, question? I lost that again? Okay, thank you. Okay. So let's review again. We've been studying birth-death systems, birth-death in equilibrium. This is the famous equation 19. It's not known as equation 19 all over the literature. That happens to be the numbering I use. But it's the birth-death equation. And they give you a very simple equation for solving all birth-death systems. Just plug in the lambda k and the mu k, and you've got it. I suggest you memorize this equation. It's fair game for the final. It certainly will be in your homework problems, but memorize that, and of course this is the way to find P0. So we applied that for a few cases, MM1, and we very quickly found that the distribution for number and system is given this way. And these formulas, it's not so much you need to memorize them for exams, although that's not hurtful, but you should know the way MM1 behaves for queuing systems. That basic behavior, that 1 minus rho downstairs, is common for basically all queuing systems. Things go to heck like 1 over 1 minus rho. As rho gets close to 1, you get in trouble. And of course, this case, MM1 just means the arrival rates are all constant, the service rates are all constant. Next case, discouraged arrival. You want the arrival rate to go down as there are more customers in the system. And we chose this as an example of how to get the arrival rate dropping as k gets big. We set mu equal to a constant. We came up with these answers. MM infinity, a worthwhile system to think about. What does that mean? Arrival rate is constant, again exponential. And the service rate goes up with the number of customers because there's always a server available for a customer that comes in. The answer for the distribution of number and the mean number is given here. And of course, this is a very natural answer. The mean response time for the system, well, you always get a server, so the time you spend in the system is your service time. And the mean service time is 1 over mu, so that's the mean response time. I made an interesting comment about using the MM1 results in the case where we use say a communications channel as the server, and then basically the thing that's serving is not time for the message, but the number of bits the message contains, so that 1 over mu c is the average service time, and we found this is a very nice way to represent the efficiency rho. And I showed you this curve which pointed out the blue picture allowed you to get decreasing response time, that's good, increasing throughput, that's good, increasing efficiency, that's good. You can have it all if you follow a path as shown by the blue curve. So that's an interesting application of some very simple queuing results. We then studied the M server, multiple server system, which means you have a constant arrival rate. The service rate grows up by K until you hit M. When you get to M, there's no more servers, so the service rate stays at M when there are more than M people in the system. This is the answer. You get, in fact, here, probability of finding nobody in the system. In this particular case, we asked the question, when does a customer have to queue? You come in, the example here is for telephony, you pick up the phone, you don't get a dial tone. That means all the other lines are being used. What's the probability that happens if there are M telephone lines in the system and the rate at which people are picking up requesting phone calls is lambda, and the average time they spend on each phone call is 1 over mu? And that answer is given here. This is the probability you go into Q in that case, and that's a bad situation. Erlang himself solved for that, and he called that his C formula. And the way you use that, this complicated equation up here, is to use a chart. If you know the input parameters, the arrival rate and the service time, and you know how many servers you've supplied to the building, then if you feed that input rate against the number of servers you have, in this case an example 11, then this right here tells you the probability of queuing. It's in a set of tables. You look it up. A typical engineering use of mathematical equations, which are complicated. Okay, so let's pick up from there now, and let's move on. I want to move to a new system now. We'll start over here. We're going to call it, again, exponential interarrival time, exponential service times, one server, but the system can only hold K people. Basically, it's finite storage. So the first question is, what happens to customers come in when the buffer is full, when all K are in the system? The model is they get lost. They have to go away. You throw them out. So they keep coming in as long as this queue is not full, the system is not full, K, capital K or less. If there's K in the system, you get bumped. Okay, so let's write that down. Refused customers are lost. And by the way, in parentheses, I'll say, if capital K equals 1, that's often referred to the case where blocked calls are cleared. And we'll use this term again in just a moment. Blocked calls, calls for which there's no space, are cleared. That's common terminology. So remember, what we're doing here is we're applying that equation 19 to a variety of examples. Here's another example. So let's ask ourselves, what's the arrival rate? Lambda. What's the service rate? Mu. What does the state diagram look like? So let's start to draw that. Let's draw a state diagram. State 0, 1, 2, capital K minus 2, capital K minus 1, capital K. And the transitions are, you start climbing up with each new arrival. But when there's K in the system, nobody else can arrive. There's no arrival rate when you have K in the system. So you keep climbing here at a rate lambda. But from state K, there's no way to go up. And of course, from each state, you can the server, the single server, will start expelling customers one at a time. So all of these are at a rate mu. So let's identify what lambda k and mu k are. I mentioned them to you. Let's write it down, okay? Lambda sub k equals lambda for little k less than equal to capital K. Strictly less than capital K. It's equal to 0 for k greater than equal to k. Nobody can come in when there are k in the system. And what is mu k? Simply equal to mu, again, for k equal 1, 2, up to capital K. Now, help me solve this. What do I do next? I want to find a little piece of k, the equilibrium probability of finding k in the system. That's the objective. Right, the inspection method. Yes, but that's too hard. It's easy in this case. What's the other way to do it? Equation 19. That's what we're studying here, remember? Okay. So we're going to use equation 19. That's why we solve for it. Okay, that's this equation up here that we had. It's this one over here. So let's just plug this equation in. So we get that piece of k equals P0 times the product from I equals 0 to what? Anybody remember it? What's the top of the product? K minus 1, thank you. And what goes in there? In general, what goes in there before we plug in the lambda k mu k? In terms of lambda k mu k, what is it? Exactly, lambda I over mu I plus 1. And now let's plug it in for the case above, for the lambdas and the mu's we have. That's P0 times the product, I equals 0 to k minus 1. Lambda I is lambda. Mu I is mu. And this is only in the range, of course, for k less than or equal to capital K. And why do I feel comfortable by saying the equal sign for k? Because if you look at this upper limit here, that goes to little k minus 1. So if little k reaches capital K, I'm talking about capital K minus 1. That's this guy here for lambda. Remember, there's no lambda going up here. So it's consistent, but I want to make sure you understand that there's nothing above there. Okay. So what is all of that? That's P0. And what does this product give me? Simply lambda over mu to the k in this range. And let's look at P0. We can calculate it in just a moment. But this is the answer for k less than or equal to k. P0, we know from the formula 19, is 1 over 1 plus the summation of the product. But we already know that product. It's lambda over mu to the k. This is for k equals 1, only up to capital K. That's as far as it goes. And now, what is this little sum I just wrote down? This is going from 1 to k. The geometric series, first term is what? Lambda over mu to the 1, right? Minus the first missing term, which is lambda over mu to the capital K plus 1. All of that divided by 1 minus a common term. Okay, now simply what we're going to do, we're going to multiply numerator and denominator by 1 minus lambda over mu, and we get that P0 is simply 1 minus lambda over mu over 1 minus lambda over mu to the k plus 1. So pk, may as well write it down, it's easy enough. It's one of two things. It's the p0, which we already know, is 1 minus lambda over mu over 1 minus lambda over mu to the k plus 1, capital K plus 1. All of that times lambda over mu to the k. And that's for little k equals 0, 1, up to capital K, and 0 for k greater than k. Done. So a simple problem, simply solved. No big deal here. Now, as I mentioned before, for k equals 1, we get the black holes cleared. That simply gives me that p sub k is equal to 1 over 1 plus lambda over mu for k equals 0. And I get lambda over mu over 1 plus lambda over mu for k equals 1, which happens to equal k, and 0 otherwise. Okay. But now I want to consider a more interesting system, and one we're going to study more than once. We'll start with it now. I want to study the system, again, exponential interarrival time, exponential service time, m servers, fixed number m servers, and a storage only for m. This is called an m server loss system. Which means anybody that comes in and cannot find an idle server is lost. Question?
For the previous example,
Yes.
can we only do this because the rate is continuous? Like, would we have issues with, yeah, for example, like, let's say you organize some service and then there's a real move, and that like might affect the rate of payment.
I didn't hear the condition. You were.
Does this only work because like the amount of will equal out? You say that people come in with rate lambda, so lambda has to be lambda.
Yes, all of this, go back to my review. All of this is basically birth-death queuing systems. When I say birth-death, I'm talking about memoryless births and memoryless deaths. Poisson arrivals, exponential service times. Nearest neighbor. All of this is near, you only go up by 1 or down by 1, okay? Now, in the exam, I made you go up by 2, remember? That's not a birth-death system. So you couldn't have used equation 19 to solve that. And how should you solve it? Balance, the inspection method. So did I answer your question? I didn't know. Okay. Sure. Okay, MMM. Okay. So new customer gets his own server. If all servers are busy, the customer is lost. Namely, thrown out. In other words, block calls cleared. Again, I'll use that phrase in a more general case now. Okay, now I don't really have to draw the state diagram, but I'd like to do it to give you a good feeling for what's going on. It's unnecessary to draw the state diagram because we could just plug in, figure out what the lambda k and the mu k are and plug in. But I'd like to draw the diagram anyway, so let's do it. Okay. 0, 1, 2, up to little m minus 2, m minus 1, and m. And we get arrivals from 0 to 1, from 1 to 2, etc., from m minus 2 to m minus 1, m minus 1 to m, and we get departures. So let's start to label this thing. The arrivals all come in at a rate lambda, so every one of these births is at a rate lambda. But let's look at the departures now. At what rate are people leaving from state 1 down to state 0? I heard it? Mu, exactly. At what rate are people leaving when there's 2 in the system? Louder? 2 mu, exactly, because there's 2 servers busy. So all the way up here, we get m mu, and here we get m minus 1 mu. So this picture helps us write down the lambda k's and the mu k's. You don't really need it, but it sometimes is helpful to see the picture. So let's write down what lambda k is. Lambda k is equal to lambda, as long as they're allowed to come in, as long as k is less than m. But at 0, they can't come in if k is greater than or equal to m. So I need the lambda k description. Now what is mu k? Mu k is equal to k in the system, or what rate are they dying? K mu. Okay, and that's up for k equals 1, 2, up to m. Notice I left out 0. There's no death when there's nobody in the system. Okay, so there we have it. That's enough to apply equation 19. So let's do it. This equation 19, as I say, is very powerful. It solves an infinite number of systems. So let's write it down. P sub k equals P0 times the product, I equals 0 to k minus 1, of lambda I in this range, which is lambda, over mu I plus 1. Mu I plus 1 means I plus 1 mu. Namely, when I is I plus 1, this becomes I plus 1 mu. Okay. And that's equal for k less than or equal to m. So what is that? That's P0. And what do I get? Lambda over mu to the k. And what else do I get? What does this I plus 1 downstairs give me? From 0 to k minus 1. Yes? You're close. What's the first term? When I is 0, I get 1 downstairs. When I is 1, I get 2 downstairs. All the way, when I is k minus 1, I get k. 1 over k factorial, exactly. Piece of cake. What's P0? Let's write that down. That's, again, it's 1 over 1 plus. Again, it's going to be the summation of a product. Summation is over k equals 1 to infinity. Notice it's from 1 to infinity. Where's the 0th term? It's that 1 up front. Because it's P0, we're multiplying, okay? Times the product, I equals 0 to k minus 1, of, what are the terms now? Lambda over I plus 1 mu. Same thing we had before. Okay. So what does that give me? This thing, this is simply the sum from 1 to infinity. And what did we get a moment ago? Lambda over mu to the k, 1 over k factorial. And what does that give me? Can I sum that? I'm sorry, it's not. Um, yeah, that is from 1 to infinity. I'm sorry. The sum is from 1 to m. That's why I paused. It's not to infinity. Otherwise, I know that sum. It's from 1 to m. And that should be up here, too. Up to m. That cannot be summed. For that, you need tables. And you may be able to see where we're going with this. So finally, we get that P0 is equal to 1 over the sum. Now I'm going to put in 0, because that includes the 1, to m of this funny thing. Lambda over mu to the k, 1 over k factorial. Now, what's the probability that there are m in the system? Because that's the probability, not only that all m servers are busy, but it's also the probability that an incoming call is lost. And that's what we want to calculate. We want to make that small. And that's equal to the following from the equations above. It's lambda over mu to the m, 1 over m factorial, over this funny sum we got stuck with, summation from k equals 0 to m of lambda over mu to the k, 1 over k factorial. Well, we can't do much with that, so how are we going to use it? The way we did Erlang's C formula, we're going to put into a table, solve it once and for all, and plug in what we needed. So let's first of all point out that this is called Erlang's B formula. And it has a definition, a notation, which is capital B of m, the number of servers, and the input parameters lambda over mu. That's the input rate, basically. And this was derived by Erlang more than 100 years ago, in 1917. So let's pull up now what we need. I've got it already stored for myself here. Let's put it on its own page. That's what it looks like. You only have to plot it once. Now, how do you use it? Suppose you know the input rate, lambda over mu. These are given constants. Lambda is the arrival rate of telephone calls. 1 over mu is number of seconds of each telephone call, 3 minutes, 5 minutes, 1 minute, whatever the average for the population is. So you know that. Suppose that turns out to be 2. And suppose you happen to build in 6 telephone lines. Then you just run this line, obviously, up here, till you hit 6. You come left, and that's the probability of loss. That's this piece of m we just wrote above. These tables exist, and that's what telephone engineers use. And if you want to make probability of loss very small, this is pretty high. This is over 1%. That's pretty high. So you probably want to, how would you improve that? Suppose you had this traffic, you couldn't change the traffic. How would you improve the performance? Yes. Well, let's just 6, 7, 8, 9, 10. Here's the line for 10. I think I'm doing it right. It'll happen way down there, right? And this is a log scale. And that'll be the answer here. That's the way engineers use this. They basically, they know this, the arrival rate for the population, the building. They know what probability of loss they're trying to achieve, and they insert enough lines to get that. Very easy. So now you can get a job. Don't worry about AI. Okay, there's a job as a telephone engineer. My wife actually did this one time too. She was working. She was a social science major, but she got a job after a bachelor's degree as a helping telephone linemen insert lines. So she's sitting in this office, and these guys are up on the telephone poles, you know, these big husky guys with all this stuff, and they're hanging up there, and they use the line to call into the office and say, look, what kind of a repeater do I need here? And she'd answer, and they'd say, I got a chick. You know what a chick is? Who knows what a chick is? Go ahead. A girl. Okay? And she said, yes, you do. And she'd tell them what to do, and pretty soon they respected her. Anyway, you don't need that story. Here's what you do to get the lines. Okay. Next, let's go to another application. I mean, we can keep doing this forever. We're going to do it for a while now. Let's go to another case, M1, classic parts and arrivals exploration service, single server, and I'm going to put a double dash here and a capital M. The fact that there's nothing in this, what should go in right here? The size of the buffer, the maximum number in system. If there's nothing there, what do you assume it is? Infinity. But I am telling you, this is the number of customers, the population size. M does not mean memoryless, it means M, 25, some number. Okay. So let's consider that. So the name of this thing is a finite customer population. That's the main thing we're bringing in here. Okay. Now let me draw the picture for you. You've got a bunch of members of the population. I'm going to put them over here. M of them. I should have drawn my pretty circles. I'll do that. Okay. Now these people sit there thinking up, say, work for a computer system or messages for a network system, okay? So what I'm saying is, when they're over here, they're in the thinking state. And when they generate work for the system, they feed it into the system. So let's draw a system. This is what I'm going to call either a telephone system, a computer system, as a network system, etc. And when one of them generates some work, they feed it in and they join a queue. Let's think of it as a single server system. So I'm going to draw the server right here. And of course, everybody's doing that. So they're all coming in this way. They're sitting here thinking of work. When they finish thinking, they jam it into the system. And if the server is free, they get served immediately. And if it's not free, they join the queue. And then they get served. And let's assume that the service time on average takes 1 over mu seconds. When they're finished being served, well, first of all, while they're being served, they can't work. So they're either thinking or they're, I'll say, in the system. So each user is either in thinking state, think of a job, you're in the system. When the job is finished, you come back and start thinking again. So it's a kind of a feedback system. So you pass through the system, you come out. As soon as you finish getting served, you come back and you begin thinking again. Now, let's assume that it's exponential service. In fact, that's what I said over here. It's exponential service. And I'm implying that it's exponential thinking time. So the time you spend thinking is at a rate lambda, and the average thinking time is 1 over lambda, because the thinking rate is lambda. So that's where and it's exponential. Okay, so before we try to analyze this, everybody understand the physics of the system. This is a finite population system. There's m people. Either they're thinking or they're being worked on. Namely, they're in the system. So they cycle around forever. This is referred to the finite. Now, if we let capital M go to infinity, this would look like an exponential arrival time. Because when they're finished and they come back, they just join an infinite population. It's as if the population size doesn't change. The whole group is coming at some rate. The average rate coming in, we don't know. It's not m times lambda, because some of these guys are thinking. So it depends upon what the probability of various numbers thinking are. So if I give you this, if you want to apply equation 19, you got to do one thing. You got to find lambda k and mu k. And you're done. So let's try to do that. What is lambda sub k? Okay? What does k mean, k in the system? Okay? Well, if there's k in the system, how many are thinking? M minus k. And each run is thinking at a rate lambda. So the input rate is lambda m minus k. Okay? And that's for 0 less than equal to k less than equal to m. And 0 otherwise. And what is mu k? Well, you're always being served at the same rate mu, so that's k equals 1, etc. 1, 2, up to m. Okay. Now, we could, if we wanted, and we will, draw the state diagram, but it's not necessary. But let's do it anyway. It seems to give a little crutch, if you will. So let's look at state 0, state 1, state 2, state capital M minus 2, M minus 1, M. Let's do the circles around these things. And let's put in the fact that we grow from state 0 to 1, 1 to 2, etc., M minus 2 up to M, and we come down from each of these states. And now I want to label them with the rates I just wrote on the page above. Okay? So, if there's 0 in the system, at what rate are people entering the box? Are they arriving? Say it again? M to M. What is that? Oh, M lambda, exactly. All M are thinking, so there are M of them, each coming in at a rate lambda. And what's the next, from 1 to 2, what is it? M minus 1 lambda. And from M minus 1 to M, there's only one guy that's thinking. He's coming at a rate lambda. The state below that is 2 lambda. And all the service rates are mu. Now here's an interesting quiz problem, which I won't give you. Suppose I gave you the state diagram. Could you create a physical system for which that's a state diagram? This is not the only one, but this would be one. I'm thinking that if you wanted to model the system in front of you right now, you'd have to go through the thinking we just did. So there's an engineering part, a physical part, to go from what you're trying to study to the system you want, and then to solve it. Well, we know how to solve this. But there's two steps. From the physics to the model, from the model, solve it. Equations. We're going to use equation 19, of course, so let's do it again. Any questions about the fact that this model gives that state diagram? And by the way, this is not an unimportant model. This idea of modeling finite populations comes up very often in many systems. It comes up in computer systems, and it comes up with what I like to call finite resource computer networks. So it's not just drawn for my pleasure. It's real. So pk, equation 19, okay? It's a fen p0 times the product, I equals 1 to k minus 1, of lambda I. What is lambda I? M minus, if it's lambda I, is m minus I times lambda, correct. And the mu is the mu. Mu k is mu, okay? And that's only for 0, less than little k, less than equal to m, capital M. So we can do that. That's equal to p0. We get a lambda over mu to the k. And what else do we get? Well, upstairs we get basically, when I is 1, we get m minus 1, etc. We're going to get an m factorial divided by some stuff, namely m minus k factorial. And I made a mistake in that product, and I just noticed it when I tried to figure out what the range is. There's a mistake in that product on the next to last line. I didn't do it on purpose. It was a mistake. Yes. Yes. She started 0. Starts at 1 when you go for P0. Okay? And that's why it starts at M. When I is 0, it starts at M, M minus 1, M minus 2, down to M minus K plus 1. When I is maximum, K minus 1, it's M minus K plus 1. That's why you start dropping off the other terms down here. Okay, that's done. Okay. And for the same range. And P0 is equal to usually 1 over 1 plus the sum from k equals 0 now up to capital M of our friend lambda over mu to the k times m factorial over m minus k factorial. Okay. Now, it turns out from this equation, I'm not going to do it, you can figure out the average number. From average number, you can find the average time in system using Little's result. Okay? And you're going to get the following expression. Let me pull up the picture I want here. Turns out that instead of capital T, I'm going to normalize it by T over 1 over mu, which is mu T. So I'll write it here. This is mu T. And this is M. And T itself looks like that black curve. And that's a rather interesting curve. Notice it goes linear when m gets big relative to the lambda over mu at a slope 1 because it's normalized. And it starts off with 1. It's pretty flat in the beginning. And it goes linear here, which says there's something going on in the system. And the transition is happening around this number, which is related to the parameter of the system, which I'm not giving you. But it turns out if you want to make an approximation to that black curve, a good approximation is the dashed lines. It's flat until it goes linear. And you wonder what are the equations for those lines, and you can find them. And it's a very useful approximation. And it turns out, and I'm talking about an engineering application here, you can recognize that what we just did for mu t, this curve has a good approximation, and we understand its behavior, and the critical point occurs around something called when the number in system is m star, which again has physical meaning. I'm not going to take you through this. I want to point out that these silly little equations we're playing with here have good interpretation in real systems. So in some sense, what I'm saying is you start with the physical model. Here's a model. You then go through what the mathematical model should be. You solve it. You look at the results. And then you try to use those results in predicting the behavior of the physical system. And sometimes you need approximations to help you. I mean, these equations are not too bad. But they can get very hairy. And when that happens, you look for approximations, which you can use by back of the envelope. So I'm trying to give you not only the mathematics queuing theory, I want to tell you how you're going to use this in practice. Take a model, take a physical system, model it, solve it, look at the answer, try to interpret the answer, and use it. And if it's not a simple answer, try to find an approximation which is close to it. So you get rules of thumb that you can keep in your head when you go driving or showering or falling asleep. And what I'm saying, I'm just casually saying that, but I mean it. You need to have these things living in your head, not on your phones or on your computers. In your head, so you can ponder them if you want to be a good scientist. Okay. Next. Again, end of the lecture. Another one. Let's go to M, infinity now, infinite number servers. Again, enough storage and a finite number population. Okay? Again, enough servers to go around, finite population. Now, without drawing the picture or trying to draw a physical system, let's go right to the equations. What should lambda k be? Okay. Well, it's a finite population, so what I said before works, okay? When there are k in the system, you're going to basically get, that's what lambda k says, you're going to get lambda times the number that is thinking, which is m minus k. This is k from 0 to m. And 0 otherwise. What is mu k? K mu. Everybody gets their own server. There's an infinite number. Okay? But we don't need an infinite number. How many do we need? At most m, because there's only m customers. So I'm going to put this down here, k equals 1, 2, up to m, just like I limited this. Okay. So we really don't need a capital M servers. Okay. I'll draw the state diagram again, just for fun. We'll go from 0, 1, 2, m minus 2, m minus 1, m, almost like what we had before. but the parameters will be a little different. In fact, the only difference will be the mu's. Okay. So again, the arrival rate when there's nobody in the system is m lambda. Nobody, everybody's thinking m minus 1 lambda, 2 lambda, 1 lambda. But now the service rates are what? When there's capital M people in the system and they're all being served, we're dropping at a rate m mu, capital M mu. Then m minus 1 mu, 2 mu, mu. Okay. So easy, let's use equation 19. Pk is P0, again times the product I equals 0 to k minus 1 of lambda I, I just gave it to you up there, it's lambda m minus I, over basically yes, it is I. It's I plus 1 mu, right? And we can write this out. This is again the same range. P0 won't even calculate it for you. Well, let's do it. Actually, it's interesting to do this, so let's do this. Okay. This thing is going to give me what? This is going to give me P0. Again, lambda over mu to the k. And then upstairs I'm going to get an m factorial over m minus I, k factorial like before. But I got an extra factorial there from the I plus 1, which is 1 over k factorial. Let me move this over. It's getting a little sloppy here. One over k factorial. Okay, now what is this thing? Exactly, m choose k. Okay, so let's write that down. It's very simple then. So we get that pk is equal to lambda over mu to the k, m choose k. And that's 0 less than equal to k less than equal to m. And P0, if you do the 1 over 1 plus thing, it's going to come out simply this way. 1 over 1 plus summation from 1 to infinity remember, if you go too high, you're going to, it only goes up to m actually. Lambda over mu to the k over m choose k. If we work that out, you're going to get that this whole thing is equal to 1 over, after all, this is just the binomial theorem again. That's 1 over 1 plus lambda over mu to the m. So pk is now simply lambda over mu to the k, m choose k, over 1 plus lambda over mu to the m. Okay, while we're at it, let's find n bar. It's going to exercise something you know how to do. So m bar is summation of kpk over the range from 0 to m. And that's the sum from k equals 0 to m of the following ratio. We got the k times lambda over mu to the k, m choose k, over 1 plus lambda over mu to the m. How are you going to do that sum on the numerator? You studied this for the exam in your homeworks. What's the trick? Little trick. Differentiate. Pull it out and recognize what we have here. If you pull a lambda from mu out, you got k thing to the k minus 1. That's the differential of thing to the k. Okay. So you do all that, you solve it. And without torturing you too much, that turns out to be m times lambda over mu over 1 plus lambda over mu. Simple answer. Okay, so my point is you can cook up almost anything you want, and you know how to solve it. Sometimes the answer is easy like this. Sometimes it's more complicated. You may need a table, but you can write it down correctly. Okay. Well, we're not done. Oh, by the way, I forgot to set my watch, and we're now a few minutes over. Let's stop here, take a 10-minute break, and come back. Come back at 3:08. Okay, let's pick up. We have only one more I'm going to do in class, and it's the following one. Can anybody guess what it might be? It's the whole shebang, okay? It's M, finite number of servers, finite storage, finite population. It's all of it together. And so you might imagine that if you choose the right parameters, you can cook up anything we've just done. Setting k to infinity, capital M to infinity, little m to 1, to infinity, blah, blah, blah. It's all there. So we could have started with this, right? But it would be no fun. Okay. So this is finite population. Let's just write it down. Infinite storage. I'm sorry, finite storage, not infinite. What am I talking about? Finite storage at k. M server. And because we have a finite population, I want to point out that if you get lost, which means you came in and there's no buffer space, there may be more people trying to come in for which there's buffer space. In the model we're talking about with finite population, I'm going to say you return immediately to thinking again all over. You thought up a job, you can't get in, you go back and start thinking again, okay? So if you're lost, you return to thinking. That's an issue you have to ask about if you're going to do this. I'll call it the thinking state, if you will. And as I said, this reduces to all we did before except the discouraged arrivals. This does not include the discouraged arrival model. Okay, so let's do this. First of all, let's write down what the lambda k's and the mu k's are. So lambda k, well, you're either thinking or you're not, so that's easy. You arrive at a rate of lambda times m minus k when there are k in the system. As long as there's room, 0 less than the k, less than or equal to capital K minus 1. That's new. You may have to stop thinking if there's no storage, even though there's enough of you to go in, okay? And 0 otherwise. And mu k is going to equal one of two things. Either k mu, if there's enough servers, namely 0 less than k less than or equal to m. But if there's more people in the system than there are servers, then you got all servers busy, so you're being served at a rate m mu. That's for m less than or equal to k. Okay. Takes a little bit of care to do that. And because I can't resist, I'm going to draw the state diagram. Not that we need it, but let's draw it. And for this, I need a lot of space. So we're going to do 0, 1, 2. What's of interest is when we cross the point of little m. So let's go m minus 1, m plus 1. And then I have to go up to k, capital K minus 1, capital K. And I can't go beyond that. So let's draw the circles. And all of the transitions. let's label them. This first birth rate, everybody's thinking it's obviously m lambda like before. Next one is m minus 1 lambda. When I get from m minus 1 to m, how many people are thinking? It's m minus little m plus 1. That times lambda. And the next one is one fewer, which is lambda times m minus m. We'll get to the top. This last one is, remember there's k minus 1 people already in the system. So I have m minus that number, m minus k plus 1, that's m minus k minus 1, times lambda. It's a little tricky, but k gets you there. Now let's look at the death rate. When there's k in the system, and notice I've drawn capital K bigger than m in this picture, so I'm getting deaths at the rate mu, mu. From m plus 1, it's mu. At the rate m, it's mu. And then from 2, it's 2 mu. And 1, it's 1 mu. OK. So easy. Let's insert equation 19. P sub k is equal to P0 times the product. And I got to be careful where I do this. Let's first consider up until we get to m. So 0 less than or equal to k less than or equal to m minus 1. Haven't quite passed the m threshold. So it'll go from 0, as always, to k minus 1. And in that case, we know what the rates are. It's lambda times all those that are still coming in, which is m minus I. And the service rate is I plus 1 mu. And that simply gives me P0 times lambda of mu to the k. That always comes out. And I've got, again, the binomial coefficient here, mk. We saw that before. Now let's consider the case beyond that, namely from m less than or equal to k less than or equal to capital K. That's the rest of it, basically. In that case, pk equals, I'm going to break the product into two pieces now. First of all, I got a P0. The first product is the one we just used, namely from I equals 0 before we get to m. So I'm going to go up to m minus 1. In that case, we have lambda times m minus I, just like above, over I plus 1 mu. And the rest of the product, I equals m up to little k minus 1, because I'm going for p little k. And in that case, what do I get? I get lambda. The lambda keeps growing the same way. So it's, again, m minus I. But the mu's are different now. The mu's are stuck at mu. So let's write out what that is. That's P0. Lambda of mu to the k just always comes out. Then I got a whole bunch of stuff. So let's write what comes out of that first product times what comes out of the second product. First product starts with a capital M. When I is 0, this gives me a capital M, and then it starts marching down. So I get m minus 1, dot, 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 down to m minus little m plus 1. But downstairs, I'm getting the I going from 0 to m minus 1. That gives me a little m factorial. And the second product starts at I equals m, so I'm going to start with m minus m, capital M minus little m. And that starts basically growing, dot, 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 up to m minus k plus 1. That's what happens when little I equals k minus 1, m minus k minus 1. Okay, downstairs, I get powers of m. And how many do I get? K minus m of them. Okay, that takes a little bit of care, but now I can combine some things. That's equal to P0 lambda over mu to the k. Now, I'm going to add in, I'll do it in red, I'm going to add in a k factorial downstairs and upstairs. And if I do that, then in blue, I'm going to notice that this thing here looks like m choose k. And because basically what I did, and you can't see it here, but I'm going to remind you, this, I've included this as well. To get that factorial coefficient. It's m factorial divided by m minus k factorial divided by m factorial, which is mk. That's all of that. And the rest of this, I'm going to get a little m to the k minus m. I'm going to put it upstairs. So let me do that in green just to show you what's happening here. This little green goes upstairs, and that becomes m to the m minus k. And I'm left over, I'll write that in black, with the k factorial over m factorial. And that's for m less than equal to k less than equal to capital K. So the point is you can do it. And what's P0? Complicated. You can write it down, but it gets complicated. It's not clean. Okay. So I want to take a particular case, by the way, now. Suppose we have capital M greater than K, but K equals M. This is a pure law system, which means if all M servers are busy, if all buffers are busy, doesn't matter how many servers you have, you can't come in. So if you can't get a server, you leave. In which case, that equation simply becomes P0, that complicated P0, times, again, lambda of mu to the k, as always. And we get m choose k. And if you want to put the P0 in, you get that, well, I'll put it in for you. P0 is equal to 1 over the summation I equals 0 to m, little m, of m choose I, lambda of mu to di. This has a name. By the way, it's only good for k equals 0, 1, up to little m. This has a name. It's called the Engset distribution, just to give you some ideas that it's useful in telephony. It's a pure law system, and that's why it's of interest to telephony. Okay. Big red line. We're finished for the moment with equation 19. You can go on forever with it. Okay? But remember, it's only good for birth, death, nearest neighbor. You can't jump states. Then that equation doesn't work. That's how we derived it, okay? So what I want to do now is make a big change, and I want to go to chapter 4. We just finished chapter 3. And the topic is Markovian cues in equilibrium. We're going to write down specifically, equation 19 does not work. If we have more than birth death. So basically, we're going to use random walks of Markovian systems instead of only walking to the nearest neighbors. We still have exponential service and exponential arrivals. We still want that. Okay? So in particular, it's more than nearest neighbor. That's the new generalization. But with some structure. Remember I told you that if we want to describe a Markov process, most of them we can't solve. So we said, oh, let's go to birth-death. We can solve them very nicely. And I said there's some others with enough structure so you can get the equations. But if you gave me an arbitrary state diagram with arbitrary transitions between them, we don't know how to solve that easily. We don't have equations for that. You can do it numerically, but we don't have a good system for solving them. There are some that do solve, and that's what we're going to show you here. Okay? So first, what I want to do is talk about a general method for the equilibrium equations. And after that, we'll go elsewhere. Now, you already know what it is. Namely, it's a set of equations, pi q equals 0, where q's were the rates of probability moving. Now, for the queuing systems, in the queuing literature, instead of using pi, we use p. So it's pq equals 0 with summation of the pk's equal to 1. Now, we know how to solve that, basically. It's the balance equations, not equation 19. But as John said, it's the inspection method, essentially, okay? So, in equilibrium, flow in equals flow out. So we already solved this set. Not all of them succumb, but we can write down the equations. Can we solve them? Sometimes. So I'm going to say we write down the equations by inspection. We just balance flow. Let me do an example. And this example is in the book. Example is a three-state system. State 0, 1, and 2. And it's the following. You can go from state 0 to state 2 at a rate lambda over 2. You can go from state 0 to 1 at a state rate lambda. You can go from 1 to 2. You can go, let me make that prettier. from 1 to 2, you can go from 1 back to 0, and you can go from 2 back to 1. And the rates, again, lambda from 1 to 2, at a rate mu from 2 to 1, and a rate mu from 1 to 0. Now, does something bother you about these labels? It's a loaded question. The answer is no. But I want you to think that, oh, lambda, for out of state 0, you got a lambda over 2 and a lambda that's more than 1 lambda. These are not, that's okay, because these are not probabilities, they're rates of flow. So that's why we talk about Q here instead of, if you will, our old friend, capital P, where we said pi equals pi p. There we were moving probabilities. Pij was a probability of going from state I to state j. Qij is the rate at which you move from state I to state j. So I didn't mean to confuse you. If this didn't bother you, fine. Stay unbothered. Okay? Now, how are we going to solve this? I want to find pk. John? Inspection method. So let's do that. So let's balance flow. We'll start with state 0. Okay? State 0, the flow says mu p1, the rate in, is the rate out, which is how much? 3/2 lambda p0. And let's do a similar equation around state 1. And that equation is what? Well, I come in from below at a rate lambda p0. That's flow in. But I also come in from state 2 at a rate mu, so it's mu p2. Whatever p2 had, I'm given probability rate mu. And coming out of state 1 is what? I'm going out at a rate lambda plus mu. You're familiar with these. Now, I'm going to write an equation around state 2, just for fun. That equation will be, I come in at a rate lambda over 2 from p0, plus I come in at a rate lambda from p1, and I'm going out at a rate only mu p2. So I got 3 equations. I got 3 unknown probabilities. Can I solve? Who said yes? No. Yes, that's a 4th equation, which means among these 3, one of them doesn't matter. They're dependent. So I must add, of course, as you point out properly now, okay, I also need the summation of pi equals 1. And this equation I don't need because it happens to be redundant. It's the first minus the second. So let me call it redundant. Just need 2 out of the 3. Okay. So let's solve it. So let's see. Let's look at this red equation. What does that say? That says that P1 is equal to 3/2 lambda over mu P0. That wasn't too hard. And the second equation says something about P2. P2 equals, once I do a tiny bit of algebra, it's lambda over mu plus 1 times P1 minus lambda over mu P0. It involves 3 probabilities, but wait a minute. I already know what P1 is. That's in this equation up here. So let's do the obvious, okay? So I'll get that P2 equals the following quantity, lambda over mu plus 1 times P1, which happens to be 3/2 lambda over mu P0, all of that minus lambda over mu P0. But now I've got P2 in terms of P0, and so it simply comes out to be bracketed, add all that together, lambda over 2 mu plus 3/2 lambda over mu squared. All of that times P0. And I know from what John told me, all the probabilities add up to 1, so I'm going to say 1 equals P1 plus P2, P0 plus P1 plus P2. So let's write that down. It's P0 times 1. That's the P0. Where's the P1 term? That's this one is a function of P0. This one in terms of P0. And the P2 is this one in terms of P0. So all that's under P0. So I get plus 3/2 lambda over mu plus lambda over 2 mu plus 3/2 lambda over mu squared. So 1 over that is P0. Then I can go back and undo P1 with P0, and that's 3/2. Well, P1 we know is 3/2 lambda over mu P0, which I just wrote down. And P2 we know from this equation up here. Okay. The point is that was easy. There was only a few states. I used the inspection method, balance flow, and it turns out I can solve these equations rather easily. If it was a more complicated system, it may not be that easy. Now, I want to make an observation about these systems which do not have birth-death. So let's make the following comment. pk in general for these systems is equal to the proportion of time the system in the state ek. Let's write that down. In state E sub k. Now let's introduce a new variable. Let's introduce something called R sub k. You've actually seen it before, you probably forgot. It's the probability that an arrival finds k in the system. So pk is a fraction of time the system is in state k. Rk is a probability, is the fraction of time an arrival finds it in that state. So the first question is, are they the same? Are they always the same? The answer is yes and no. And I'll give you an example. So the question is pk equal to rk? And the point is, it's not always true. I'm going to show it to you. Which means if you're going to solve a system and you have either pk or rk, you're going to use them differently. Rk is what the arrivals see. Pk is what the system has to put up with. And there's either also another quantity we'll define later, which also has a question, is it the same as these? So as an example of when it's not true, let's take the system DD1. That's a system where every 1 second an arrival occurs. At time 1, 2, 3, 4, bang, bang, bang. And they spend exactly, say, 9/10 of a second in service. Come at a time 1, 9/10 of a second later you leave. At time 2, another guy comes in. 9 seconds leave, come up. Okay? Very simple system. Now, the arrivals never wait, do they? So R0 equals 1, and Rk is equal to 0 for k equals 1, 2, etc. You never wait. But P1 is equal to the fraction of the time the system is busy, which we know is rho, namely, it's the mean service time over the mean interarrival time. So 1 minus P0 is equal to 1 minus rho. And pk is equal to 0 for all others. 3, etc. So in the first case, with dd1, the probability an arrival finds nobody is 1. But if you look at what's happening in the system, a fraction of the time rho, the system has 1 in the system. So the fraction of time you're in the system, so basically P1 is not equal to R1, P0 is not equal to R0. Okay, but, a nice happy but, RK equals PK often. It's true for all queuing systems with Poisson arrivals. In fact, more than that will show that pk of t, namely, what's the probability at time t of a k in the system, that's also equal to the probability that an arrival who comes in at time t finds k, or for all t, not only in equilibrium is the point, for all time. And I'm going to prove this to you. It's a happy circumstance. Yes? Okay. What's the probability that an arrival finds 1 in the system? 0. It's always empty. Guy left 9/10 of a second, bang. But what fraction of the time in DD1 is there 1 in the system? 90%, 0.9 on 1. So P1 is not equal to R1. As an example. Very simple but powerful example. Okay. Now I want to prove this to you. What this says is that somehow Poisson arrivals take a random look at the system, because pk is the random time. pk is the fraction of time the system has k in the system. So if you take a random look, you'll find k, pk of the time, because pk of the time there are k in the system. But arrivals come in at special times. In DD1, they don't find 1 in the system. But Poisson arrivals do behave as if they're taking a random look. Here's the time axis. There are people in the changing number. It chooses to arrive, bang, at any random time. Why? It's memoryless. Last guy came in. When does the next guy come in? At a random. In fact, we showed earlier that constant arrivals, constant arrival rate, Poisson arrivals, and exponential arrivals are the same. But let me prove this. I'm just giving you a physical interpretation, okay? So let's let the quantity A of t, comma, t plus delta t be the event that an arrival occurs in that interval. Occurs in t plus delta t. And we're going to let this quantity I mentioned above, R sub k of t, be the limit as delta t goes to 0 of the probability that there are k in the system at time t, n of t, the number in the system at time t, is equal to k, given that there was an arrival there, given this event A of t, t plus delta t. Isn't that what R sub k should be? R sub k is a probability that an arrival at time t finds k, and I'm saying let delta t go to 0 if there's an arrival occurring in time at time t, and that the system had k at that time. Okay, so let's calculate that thing. Well, this is conditional probability. Let's play our usual game, okay? That's the limit as delta t goes to 0 of the ratio of the joint over the condition. Probability n of t equals k, and there's an arrival in t plus delta t over the probability of condition, the probability that there is an arrival between t and t plus delta t. Let's take that a little further now. That's equal to the limit, again, as delta t goes to 0 of the following. Let's write this condition in the equation above as a condition times a probability condition, as usual. So let's write that as the probability that A, t, t plus delta t, that an arrival occurs in this interval, given that the number at time t is equal to k, times the probability of that n of t equals k. All of that by the same condition that we had, p of a of t and t plus delta t. But for Poisson arrivals, this event is independent of that. It's memoryless. So this condition doesn't matter. Probability of arrival in the delta t doesn't depend upon how many were there at time t. Okay? So let's write that, therefore. That p, well, so basically this thing, I'll write it out here. This is simply equal to the probability of the event A, t, t plus delta t. Now look what happens. In blue, I'm going to cross the denominator out with this. And what I'm left with is simply R sub k of t is equal to the limit that I have above, limit delta t goes to 0, of the probability n of t equals k, which we call p sub k of t, QED. Rk equals pk. It's true at any time, and it's true in the limit. No? Okay. So again, I'll repeat. Poisson arrivals take a random look at the system. That was a little diversion, but it was worth commenting on. Now, the next thing we're going to do on Monday, we're going to then look at some cases of Markovian Qs which are not birth-death, for which we can get answers. And it's due to a brilliant idea of airlying once again. I won't tell you what it is. I'll let you basically worry about it or think about it or conjecture about it all weekend, right? No, do your homework on the weekend. Okay? It's a brilliant idea by this wonderful engineer. And he was actually able to create a structure using the same tools we have here, balance equations, and solve all GG1 systems. But it's complicated, and so we don't use that to solve it. Numerically complicated, but he showed you an approach to handle all GG1 systems. We're going to slowly approach GG in a more systematic way. But it just points out to the brilliance of airline, and maybe if you're really good, I'll show you the pictures of these people on Monday. Okay, they really did exist, actually. So, okay, so let's finish the class right now. Thank you.